So hi everyone, I'm David MacIver. I created a testing library called Hypothesis and still do most of the work on it, although we've got a proper team now. I'd like to tell you a bit about it today and sort of less the concrete details of Hypothesis, although we'll be using it for examples, and more why this sort of testing is great and why you should all be doing more of it. So the main thing I want to try and convince you today is that you should start, don't worry too much about the details of any of the code I show on screen, particularly when it's long like this, but I want to convince you to write fewer tests that look like this, where they are painting a sort of a very concrete story of like an exact scenario that you've spelled out. Here we've got some tests that happens to be using Django. I don't think you use Django, but that's fine. But it's got some sort of system with a project concept. You've got a collaborator limit on your project, and you want to be able to add people to it to collaborate on it. And that's roughly what this is testing, but instead of that sort of high-level description, what you've got is a very concrete story. There is a user called Alex, there is a user called Kim, there's a user called Pat. We've created this project with a specific name and a specific collaborator limit, and we've added them, each one of them, to the team. And for the purpose of human understanding, this sort of story is actually quite good, and you definitely shouldn't throw them away entirely because they give you very concrete objects to ground your understanding of the system with. But as a way of specifying the software and as a way of ensuring that it's working correctly, they're essentially extreme overfitting. They are telling what happens in a very specific scenario, and they are assuming that you can generalize from that scenario, and that if it works in these few stories and few anecdotes you've told, then it works more broadly. And it's nice to believe that, but this turns out to be a lot less true than we naively expect it to be. And so what I would like us to do, individually and as a community, is write not zero tests that look like this, but fewer tests that look like this, and stop relying on these tests as a way of trying to ensure the correctness of our software. And instead start writing tests that look more like this, where rather than telling a concrete story, sorry, I usually have this on a larger screen, so this may not be that visible. I'll talk you through the details. Where we've taken our previous test set up a specific project and a specific set of users, whilst this in the given decorator up at the top specifies instead a range of projects and a range of users. We've said we have a single project. It has a collaborator limit that could be some number between 0 and 20. We have correspondingly a bunch of users. We don't know who they are. But again, there's some number between 0 and 20. And then within the test body, we've said we try adding each to the project, and this is what can happen in these scenarios. It becomes a general purpose specification where we have described a whole range of scenarios that the behavior should hold in, and we have then specified not how that should be done, but what you should see when this happens, and where you should see errors, and where you should see correct behavior, and what that correct behavior looks like. And this test happens to be much more complicated than the very example-based testing, and the reason is that the behavior turns out to be much more complicated than the people who were writing it thought, and there turned out to be a bunch of edge cases, like what happens if you try and add the same user to the project twice? Does that affect the collaborator limit? Can you do that? And those sort of emerge in the course of testing, and because this sort of specification allows the computer to, well, not the computer, the testing library to automatically explore the range and probe at the boundaries of where the anecdotes turned out not to show the whole picture. And so you wouldn't write a complex test like this up front necessarily, but you can then use the testing to explore the specification and to grow a more principled specification. And I've now thrown you into the deep end, and we're going to now go sort of back off from the details of the code and talk about a little bit of theory. And the theory and practice. Because what I want to think about is how do we actually find bugs in the system, and how do we actually think about bugs and sort of conceptualize like what it is we're doing here. And the way that I like to think about it, which I think is a useful thing to bear in mind, even if it's not necessarily the place you all start from, is a sort of state-space view of our program, where at any given point in time, a program is in a particular state, and some of those states are good, and the program is working normally, and some of those are bad. So we can think of it as this. We've got some sort of core of good states surrounded by a sea of bad states. And in between them, there's sort of the range of things, states that your program can actually get into, the possible states. And what we are doing when we're looking for bugs is we're trying to find those outer areas where the set of possible states is impinging on the set of bad states, and something goes wrong. And so this would be our ideal scenario. The set of possible states is contained entirely in the set of good states, and this basically never happens. I used to believe in correct software, and then I wrote a testing library, and now I see broken software everywhere. So I no longer believe this ever happens, but like this is the ideal to which we want to approach. We want to constrain that the only possible things that can happen are good. And so then what we're doing with testing is that we're essentially exploring paths in state space. We start our program off somewhere, we move it about, it bounces from one state to another, and we see if it ever makes it into a bad state. And the idea is that we just basically want to cover the set of the possible state space with these paths until we have essentially exhausted the possibilities and found everywhere the bugs can lurk. I should note that this is lies, and this is lies in one important way, which, well, in several ways, but the important one that I'm going to largely ignore for the rest of this talk is that I've pretended that we can tell the difference between a good and a bad state. And the reality is that except in the most blatant of examples where the program crashes or something like that, we can't a priori do that. And so the job of tests is not to just explore the state space, but also discriminate between good and bad states. And the problem with doing this and why it's difficult is that essentially whether a state is good or bad depends on your program specification. And some states are obviously good or bad. You've crashed, you've executed arbitrary SQL that a user passed in a query string, you've showed completely wrong data in some way. Others are more subtle, and you do need to sort of think hard about what your program is actually supposed to be doing, and how you can determine whether or not it's doing that. As I say, I'll mostly be ignoring this distinction for the rest of the talk because this is something that you have to solve anyway for doing normal testing, and what I'm going to show you doesn't make this any particularly easier or harder, except in scenarios like before where you're exploring the specification and learning more things and sort of having to decide whether or not there are bugs or not. But I'm largely just going to accelerate the process there. So I've started with this idea of a state, but I haven't really told you what a state is. And I'm going to continue to leave it somewhat woolly, but it's worth sort of thinking about what we care about in states and what is and isn't a state. At the most general sense, a state is everything. Everything that happens in the universe, or at least in your past light cone, can influence what your program is doing and can have some consequence on it. And it would be nice to know that your software works correctly if a cosmic ray hits the computer and a bit gets flipped. But while this is the most accurate view of a state, it's also probably the least useful. It's quite hard to put the universe into a specific configuration in order to test it. If we sort of adopted this approach to states, then we'd essentially never get anything done. A more restricted view of this is that we think of states as just what's happening inside your computer, and is just the configuration of the computer, all of the bytes in memory, everything that's on the hard drive, etc., etc. But the problem is that this is still a very large number of states. It's smaller than the whole universe, but it's not smaller than the number of atoms in the universe, because even when computers look like this, 8K of memory is still 2 to the 8K possible configurations for just your memory, let alone your hard drive, which is still an infeasibly large number of states. We can zoom in further, and at the back you probably can't see this at all, but basically this is just some assembly that came from a perf recording of a Python program. And you can think of your state as just the program counter, of just like the current point in the instruction stream where the computer is executing. And this is actually now a bounded, relatively manageable number of states. Like, it's not a small number of states, but a small number is not. Yeah, but it's, if you've got a couple meg executable, then it's a couple million states. It's not. No, it isn't a disastrously large number, but it's also much too specific. If you're writing a C program, then this is almost okay. If you're writing a Python program, then literally none of the things that are executing are happening in this instruction stream. They're happening in the data that has been loaded from your Python bytecode. And even if you're writing C, like what the values are in memory will make a big difference. Because you can have a an almost completely branch-free program that just has, say, an assertion in it somewhere that this value is not that value, and then what happens when you transition out of that state, into that state depends on the values in memory. So we can't ignore memory entirely. We do have to consider more than just the instruction pointer. And so what we're going to do is we're going to do the standard mathematician cheat, where we go, well, it's this thing up to equivalence. And what we mean is that a state is basically a snapshot of your computer, except that we pretend that things that don't matter things that only differ where they don't matter are the same thing. So if you are writing a C program that just looks at one particular word in main memory, then your state can just be your instruction pointer plus that one word of memory. When you introduce variables and use them, that sort of introduces new states. And we just sort of will use whatever representation of states is convenient as just abstract representation of the bits of the computer we care about. And this is mostly a tool of thought. For non-trivial programs, you're never going to actually write down a state representation other than the program itself. Though if you are writing formal methods tooling, you might have some sort of internal representation of it that another program can handle. I mostly don't write formal methods tooling, so I don't do that, but it is a thing that some people do, which, again, I will not get into in this talk. Let's start thinking about how many states. Sorry, one of the fundamental things about this is that what a state is depends a lot on your program. So I'm going to show some simple C programs. This is not going to require any deep understanding of C. C is just useful here because its data types have a fixed number of bits. Like if you consider a function that takes a Python object, then that could be literally anything. It's got essentially an infinite number of states because Python is such a ridiculously complex language that a Python object could pretty much do anything when you do anything to it. While as for simple programs, at least, C has a relatively well-defined in-memory semantics, or at least we can pretend it does. So here we've got a function called doAthing that actually doesn't do a thing. It does nothing when you pass it a single integer argument. And under most computers and most compilers, an integer has 32 bits. So this function has essentially 2 to the 32 states. Like, all that matters is the value of that integer variable. Or certainly the things that aren't the value of that integer variable don't matter. And then it takes that argument, ignores it, and it returns. So although it's got 2 to the 32, or about 4 billion states, really it's only got about one state, because each of those 4 billion states are equivalent. If we were to then add an assertion to it that just asserts that I is not equal to 42, it's still got 2 to the 32, 4 billion sort of different values in memory that matter, but now that's about 2. Like, the only states that really matter here are the ones where I is 42 and the ones where I is not 42. And so this is still a relatively manageable number of states compared to our 2. Well, I mean, 2 is a very manageable number of states, and is much more manageable certainly than 4 billion states. And so this doesn't seem too bad, but the problem is that these numbers are multiplicative, they're not additive. So if we consider this extended function, which takes 26 Boolean arguments, obviously don't write a function that takes 26 Boolean arguments, but it's a good representation of sort of the configuration space of a more complex program. There are certainly 26 true or false conditions that vary in most non-trivial programs. And each of these arguments, all we do is we just call a function if the argument is true. And so this has 2 to the 26 different possible configurations it could be in, 2 for each of the 26 arguments. And that's about 70 million, which seems relatively small compared to our 4 billion earlier. But the problem is that depending on what these functions do, they could interact with each other arbitrarily. And so in principle, we could distinguish any one of these states from each other. So for example, each of these might be setting a particular global bit somewhere, and then we might be asserting we've not got a particular bit pattern at the end. And so unlike our previous examples, once we start doing more interesting things, we can distinguish these states, and we can start to find, and so each of these 70 million states is actually interestingly different, and so we actually have 70 million states here. And another thing to notice about this example is that it's extremely easy to get 100% code coverage on it. So this, because you can try 2 things, and you can try passing all the arguments as true and all of the arguments as false, and voila, you've got 100% code coverage. So if you've got an intuitive sense of how hard it is to get 100% code coverage of your program, for this function, it is 35 million times harder to get full coverage of the state space as it is to get 100% code coverage. And so when I said that tests look like this, and they sort of are exploring paths in our state space, it turns out that's a lie. Tests look like this. They are covering just like tiny dust motes in the set of possible states, and it's essentially entirely impossible for us to even dream of covering the state space with tests, because the state space is so incomprehensibly huge that even in our simple examples, like merely doing 5 orders of magnitude more testing is not enough to get close to doing it. And the tools I'm going to be showing you don't help with this as much as like one likes to imagine, because, or they don't if you take the direct approach of just trying to do more testing, because all that means is that we take our dust motes and we turn them into slightly larger dust motes. We're doing 1,000 times more testing, but we need to be doing millions or billions or like essentially an infinite amount more testing if we want to get this sort of complete coverage of like everywhere our program could possibly go wrong. So everything is doomed, testing is impossible, let's just go home and stop writing software. I mean, this is sort of true. Like, as I said at the beginning, I don't believe in correct software anymore, and the essential impossibility of testing it is one of the reasons for that. You can do formal verification, which reduces the number of bugs into basically the bits that you haven't verified and the questions you've got to ask, but it's almost worse than impossible to do formal verification right now, because instead of impossible, it's just really hard and really expensive, most importantly. But there are things we can do with testing that sort of get the situation a bit back under control, and even if they don't give us correctness, they give us a lot more correctness than our current testing can do, and start to get it to the point where we can worry a bit less and hopefully spend less time on call being woken up by bells. And the thing that Hypothesis is built on, and a lot of the tools in the space are built on, is what I call the fuzzing assumption. This is a term specific to me, but I think most people who work on these tools will rapidly know what you mean if you talk about this sort of thing. And the starting point of the fuzzing assumption is that you break your system up into small parts, like what you do in any testing. Like this is just saying you unit test stuff. It's not a deep principle. And those parts might be something like a parser or a specific function or so on. But the point is that you're restricting yourself to a relatively constrained part of your program. And once you do that, there are 3 types of bugs. And like I said, this is an assumption. It's not strictly true, but it works surprisingly well. The first type of bug is the obvious bug. These are bugs where you just, like, there are a couple of natural things to try, and one of them works. So here's a very simple test using hypothesis, where we're taking a list of integers, and we are asserting that the minimum of the list is smaller than the maximum of the list. It seems a perfectly reasonable thing to test, or not necessarily to test. You might think it's too obvious to test. That's another thing I don't believe in anymore these days. But in this case, the thing it's claiming is actually true. But the test has a bug in it. It's an obvious bug. It's that if you pass the empty list, then it tries to take the minimum of an empty list, and it fails as a result. And this is the kind of thing that I mean by obvious bugs. Like someone somewhere has forgotten that this value can be missing, or that this value could be negative. And there's like a very small configuration space where you can just essentially poke a couple of weird values into every function there, and you're going to find something that someone has forgotten. The second category of bugs in our fuzzing assumption is bugs that are common. We often think of bugs as being like these weird corners of the search space that you need to get in very specific circumstances to trigger. And this is sometimes true, but as we'll see in a moment, but it's mostly, like most bugs, you can just try 100 or 1,000 times harder, and you'll eventually find it because they turn out to occur in like 5% of the search space or 1% of the search space, which isn't super common. It's not the happy path because we've already tested the happy path and we didn't find a bug in it. But it's like the error handling path, or the path where a slightly weird thing happens. And fuzzing is very good at finding these sort of bugs because it does do just this 100 or 1,000 times more testing, and it does then trigger things. So I'm going to give you some examples of finding this in the wild. Here is a library called binary or not, and it tries to do, what it does is it takes a file or a byte string and says, do we think this is probably intended to be text data? And this is an intrinsically impossible thing to do, but it's a heuristic checker, and it does a surprisingly good job in the wild. And so here what we're doing with hypothesis is, and this bug's actually from the days where hypothesis was a lot less smart than it currently is, and so it really was just randomly throwing binary strings at it and seeing what happened. Essentially cat-dev-u random levels of testing. And what I found after some minimization was this small string, which when you just pass it to binary or not, you don't assert anything about the value, you literally just call the function. And binary or not crashes with a Unicode decode error. Carmack codec cannot decode byte OXAE. And what turned out to be going on here was a fun bug where under the scenes what's happening is that binary or not is asking another library which is doing heuristic checking called cardet, and saying, what encoding is this likely to be in? And cardet returns, I am 100% certain that this is UTF-832 LE, meaning 32 bytes per code point, 32 bits per code point, little ending encoding, if you care about that detail. And binary or not says, okay, well, it's 100% certain, so that must mean I can just decode it as that encoding, and then just check if it's got weird code points in it. And it turns out that when cardet says 100% certain, it doesn't really mean 100% certain. And in particular, it's never actually checked if you can decode it as that. And sometimes cardet's heuristics misfire and say, actually, and so you get something in this scenario, which binary or not didn't know to check for, so it got this wrong. And this is one of the big spaces of where you get these common bugs, is when you've got this sort of assumption mismatch across two boundaries, where people agree on sort of the really common parts of reality, because like it's hard to not, because as soon as you try something, if you disagreed on something basic, you're going to see that. But you don't necessarily think and check in these slightly odder corners, and you don't necessarily think to ask about it. So unless you have somehow miraculously come to the same conclusion as the other person, or you already knew this was a thing you needed to check for, you get these odd edge cases where assumption mismatches happen and bugs lurk. And fuzzing is really good at finding those. I don't have a deep reason for why that should be, other than that it turns out this happens a lot, but in practice that seems to be the case. Is the low importance bugs. And this is a somewhat facile definition. And the reason why they're low importance is because they're harder for other people to find than they are for us to find. Common bugs are easy for users to run into. Obvious bugs are easy for dedicated attackers to find. But bugs that are neither common nor obvious, like unless you have access to the source code and actually can, by inspection, see that it's there, you're probably not going to find it. And as a result, we don't care about it so much, because bugs really only matter when they have real-world consequences. And bugs that are neither common nor obvious do have real-world consequences, but they start to be rare enough that they aren't necessarily worth the cost of finding. And examples like this are things where you have some magic constant that you got an assertion that this value is not equal to that. If you're looking at the code, you can go, aha, what happens if I test if that magic function? If you can run the program in some way under like emulator or if you need a disassembler, you might be able to extract it. At some point, Hypothesis is going to be able to start making this test fail, and I do know how to do this. It's just because they're low importance bugs, I haven't cared that much so far, so I haven't made it do it. And so right now, this test will pass because essentially there is no way to spot the magic constant at runtime. And so this fuzzing assumption means that we can actually get quite far with this sort of testing, and we can shake out most of the bugs that matter to us, even though exploring the actual real huge search space is mostly impossible. And so what we can do is we can sort of carve out these regions in the search space of everything that is near to some point we've tested, and say, this region is good. And we can say that without it being strictly true. It's not a region that we have proven everything in it works, and in this case it happens that everything in it works, but it isn't necessarily the case based on what we've done. And we can just sort of have faith that our testing is good enough around there. And then we can sort of daisy chain this outwards, where we've explored that region, we've explored this region, and sort of form this chain of inference where we believe that everything around here is basically good. And eventually we work our way out into this region where a failing case becomes common and our tests find a bug, hooray. Or not hooray, depending on whether you're coming from the perspective of someone who is testing or someone who is developing. This is again lies. And the main reason why this is lies is that exponential fall off is a thing. So even if every one of our regions of testing we're 99% confident that we've got the correct answer, then sort of this daisy chaining through a number of steps of inference means that 99% confidence relatively rapidly drops off to 50% confidence, or 49% confidence in this case. And so this is still not giving us correctness, but it is giving us a much greater guarantee of correctness than we expect. And also 70 levels of inference is actually a relatively large amount of inference. But nevertheless, this is not sufficient to explore a large search space, but we have some other things that can help us out. The first is simply decoupling. I'm not going to talk about this in depth because this is what you're already doing in your test, like breaking things up into modules, breaking things up into unit tests. And the nice thing about decoupled software is that if you have two parts of your system where the states don't interact, then the number of states is effectively additive, not multiplicative, because you can treat for the purposes of testing, because you can treat a state in a compound system as containing a state from one part and a state from the other part, and if both halves of those are adequately tested, you can assume that the non-interacting things work equally well together. And so that lets us break the system up into smaller configurations, and so not rely so much on these long chains of inference, because we get these parts for free. The second more interesting part is state collapse, which is that there are a lot of things where we introduce a huge number of states, but as long as we then make it out of those states successfully, and none of those intermediate states have bugs in them, then then the number of states collapses back down again as we throw away data and we don't have to use anything else. But here's a simple code example that demonstrates this. This is very stupid code, you wouldn't write this, but you can imagine it as standing in for something more complicated. So we take a list, and we create a list of the numbers from 0 to 99 inclusive. We shuffle the list, and then we sort it. And the reason why this demonstrates state collapse is that when we shuffle the list, we introduce 100 factorial possible different permutations of the list, which is an impossibly large number. It's significantly more than the number of atoms in the universe. But then we sort it again, and now there's only one list there, and then we return that. So even though we've introduced this really large number of intermediate states, they never escape the function we're in. The number of states introduced by this function, as long as the function itself does not contain a bug, is only really 1. So the number of states can collapse as well as explode, and this is one way of keeping our search space bounded. And the way to these collapses sort of happen in real code is what if I were going to be more of a mathematician. I am a mathematician, but I'm largely pretending not to be for the purposes of this talk. I would start talking about commutative diagrams and category theory. But all this really means is that you can take different paths that get you to the same place. And so looking for things where the combinatorial explosion essentially gets collapsed because it doesn't matter which way you got here as long as you're here. And so you can use the fuzzing assumption to get that the intermediate states all work because you tried enough of them. And then rather than having to go to continue to rely on that, you now know that you can start in this new single good state, and you can rely on just testing from that one state. So often, like taking sort of things you can test, you'll get this kind of exponential growth where I make a choice, then I make another choice, then I make another choice. And at each point, the further you get on, the number of choices you could have made to get to this point is 2 to the n, which means that very rapidly, unless you're doing a truly unnatural amount of testing, you're covering a really tiny section of the state space. But if instead what happens is at each level you collapse back down again, then the number of states you have to test at a given level is just linear in the depth of the testing, and is relatively bounded, and a relatively small amount of testing can get us there. If you think back to the coverage example earlier, what happens when you've got this sort of collapsing is that 100% coverage mostly is enough. Like, it's still not quite enough because for various reasons, but it's within an order of magnitude of enough. And you're sort of avoiding this exponential growth problem. Which leads us to the big question, like, do states in our programs actually collapse? And in one trivial sense, they do, because you have all these functions which are introducing intermediate variables, and those intermediate variables, they're local. They go away after the function's finished being called. So a lot of states collapse like that. But I mean, depending on what your function is returning and what your function is doing, it's still introducing a lot of states. If your function is introducing an integer and you're ignoring all of the intermediate states, then that's 2 to the 32 states it could be introducing. So that sort of local sense of state collapsing isn't really enough necessarily. But there are a bunch of other sort of interesting ways that states can collapse in the course of our program running, and they do end up creating a certain amount of boundedness in the amount of work we have to do. But we need to know whether they're there or not. How do we find whether they're there? Well, we test it. And again, we lean relatively hard on our fuzzing assumption and sort of assume that if states were going to not collapse in these scenarios, then then hypothesis or whatever testing tool we're using could find that. And one natural location where this happens and is really good for testing is when you're serializing data. It sometimes feels like 90% of the point of modern programming is basically taking data in one format and turning it into another format. So if you've got your sort of production system, you've got data you're exposing over an API, and you've converted it to JSON, and people are posting JSON back to you. It may not be JSON, it may be something more sensible, but it is some textual or binary format. Then you're storing it in a database, and you're getting it out of the database. And does your program behave the same way if it's using a freshly created object or an object from the database? Hopefully. And what you get here is you get this very nice pattern of basically that is very easy to test for, where you are essentially doing round tripping. You are converting something into a new format, converting it back to the original format, and asserting that you got the same thing back you started with. And this is sort of the number one interesting property-based test that people tend to add to their programs, and it almost always runs. I won't go into the details of the bugs I'm going to show you too much, but basically here's one we found in Mercurial, where it has an encoding where it needs to represent binary data as Unicode data, due to what I'm sure seemed like very sensible reasons at the time, and is using UTF-8b, which is a format for doing that. So we're asking hypothesis, give me binary data, convert it to UTF-8b, convert it back to binary again, the original byte stream, and assert we got the same thing back. Originally this just crashed because it turned out that Mercurial was producing invalid UTF-8 when it was doing that. Once they fixed the crash, they found this more interesting problem where I think it was dealing incorrectly with repeated strings of bytes or something. And I believe the implementation is certainly now correct to the point where hypothesis can find it. But I think if they'd ever run into this in the wild, it would have wasted a lot more time debugging. I'm going to show you another fun one because I like showing off bugs that hypothesis actually found, which is in dateutil. It's datetime. By the way, there was a tradition for a long time, which I think we've now sufficiently victimized all of the libraries that this doesn't happen anymore, but basically every time someone was doing a hypothesis talk, they would find a new bug in a date and time handling library. This is one, I think, that is the origin of this bug. This was, I think, possibly from the first generation of this talk, which I've reworked things a lot from. So date times, there is a one true date time format, which everyone should be using for everything, which is the ISO standard. And what we're doing here is we are converting a date time to the ISO format, we're parsing it back out, and we're asserting that we get the same thing again. Here what we're actually doing is slightly more complicated, which is that we're converting it to ISO format again and asserting that the string representations are the same. The reason for that is because date time comparison in Python is weird around time zones, and this is a reliable way of testing that. And we found a great bug. In single-digit years, if the number of seconds is the same as the number of the year, then the parser will swap the year and the month. I believe this is still not fixed. I think they're planning a big reworking of the parser and are holding off on fixing this one until they get that. I haven't looked into why this happens because honestly, it's funnier if I don't. But yeah, and this sort of serialization bug abounds though. You can get problems with converging any sort of interesting data types. I think Daniel was mentioning something about converting floats to and from JSON. I tried to replicate that from this talk and I actually couldn't, so I may have to talk to you about this later. But the point is that converting to textual formats is often complicated and it's often lossy. And this is often a great way of introducing these sort of chains of bugs into your software where basically everything seems to work fine until it spontaneously doesn't. And the reason is because you thought two states were the same when they actually were different, because it mattered where the data was coming from in an important way. The other big thing that you can do is normalization. Often a function normalizes something. So the sorting example we saw earlier was this. It's the output only depended on the sort of the list. So n factorial states have collapsed into one state because this value can essentially be collapsed into a much smaller number of possible values that we actually care about. This one's not a real bug, but it's representative of a bunch of interesting real bugs that hypothesis found and requires less setup to explain. Which is, suppose we have users of our system. Hopefully we have users of our system. What we want to do is we want to stop users. We want to support Unicode usernames because we're a properly internationalized company. We do, and we understand that people have weird accents in their names and stuff, or they are from Far East Asia and have completely different character sets. Unicode is good for a number of reasons, but there are a lot of sort of different Unicode strings that look the same. You might want to change. You might change the case in your username. You certainly don't want uniqueness of usernames to be just string-wise identical, because you can have there are a whole bunch of ways that can go wrong. So we canonicalize it. First of all, we turn it into a Unicode canonical form, and we then lowercase it so that it's case insensitive, and so that we don't allow username spoofing by this sort of changing of case. And then we check once again the state space collapse. We check that if we change the casing of our name, which we do by uppercasing this time, then we can we get the same result back. We were testing this sort of collapse as the input to the normalize function, and this finds a bug. And the reason is because Unicode is hard, and the correct thing to do would have been to use not lower but casefold, which is the canonical way of turning Unicode strings into a case-insensitive representation. And here we find that there are Unicode characters that if you uppercase them, then they are, and then lowercase them again, you get a different result. I believe, if I remember the correct name for this, this is a lowercase Latin I without dot. Not to be confused with the equally important lowercase Latin I with double dot, maybe, which found a different Unicode-related bug in the Python regular expression module. And what happens there is that changing the case changes the number of code points. Here we have the much simpler problem that basically uppercasing this letter turns it into a normal capital I. Lowercasing it again turns it into a normal lowercase I rather than the special form. And this sort of bug is actually really important. Spotify had a major account hijack bug. Not so much from this, but from the Unicode normalization. But getting normalization wrong really does cause interesting problems in your software, because essentially sometimes it works and sometimes it doesn't if you get it wrong, and it will work in the happy case, but there turn out to be like lots of unhappy cases in Unicode. The other thing you can do, which doesn't strictly fall into the state space collapse, but is important paradigm, but is important enough that I want to sort of emphasize testing this, is basically making assertions about the range of outputs of your functions, because outputs of your functions become inputs to other functions. And this goes back to the decoupling thing, where you can essentially now test one function's output and one function's input, and as long as the output always falls in the right range that you're testing, you can worry less about testing the two of them together. Not at all, but less. So here's an example that is extremely unkind. I'm not going to say mean because that pun is beneath me, and has broken essentially every implementation of the arithmetic mean I have ever thrown it at, which is that you want to calculate the average of a list of numbers, and you want to assert that this average lies in a sensible range, which is that it should be between the smallest number and the largest number. That seems perfectly reasonable, yes. Floating point numbers are even less reasonable than Unicode. Unicode at least has good reasons, and those reasons are people are complicated. Floating point numbers are basically made of computers. And this one is the Python standard library statistics.main, which has broken in the least bad way of any implementation I've seen at it, which is just that it gives you an error when things are going to go wrong rather than giving you a wrong answer. But if you try this on NumPy's mean calculation, for example, then you'll get things essentially arbitrarily far out of bounds because of rounding errors. And this can then sort of compound problems because you expect this property to hold, and so when it doesn't hold, you get your program into an invalid state further down the line. And having these sort of range checks all around your program and all around your testing just helps keep everything into like a sensible set of state transitions and helps constrain how badly wrong things can go, as long as you've tested both the output range and the valid input range. Like I said before, none of this is going to get us correctness. It's like ultimately we are still testing things, and testing things is fundamentally doomed to only find what we look for. And without vastly more advanced tech than we currently have, trying to do better than that is not really accessible to us. But this is still better than almost everything that people are doing without this sort of tech, and gets us far closer to correctness than I think we could reasonably have expected before going down this path. And more importantly than correctness, what this gives us is confidence. It's not, we're not shipping correct software, but we're shipping software that's probably not going to fall apart in our faces, blow up in our faces. And it's probably not going to fall apart when people sort of try and use it. And because it gets us to the point where our ability to find bugs is better than the people who are likely to be using it. And that turns out to be a huge booster. And it turns out to make the entire process of software development much happier. Certainly, I can't believe I used to write software without this sort of tooling, because every time I have gone back to a project which I thought was really good and thought worked really well, and tried to apply this sort of tooling on it, I'm just like, how did this ever work? And this conference is really important because it means that not only are we getting software that works better, it frees us of a lot of fears. There are things that I'm entirely happy to try these days, simply because I know that if and when I get it wrong, I can detect that that's happened. And so things that previously seemed big and scary are now not necessarily within my reach. Like, I might try them and discover that actually I was right, they were big and scary, but I will find that out now and not after I've shipped it in production. And usually what I find is that they're not nearly as hard as I thought they were. Although I have a recent patch where I was just like, here, I made you a hash table that I'm not necessarily sure the recipient appreciates as a result of this. So it's a mixed bag, but it was a really good hash table. And that is pretty much all I want to say for now. This sort of testing is really useful. If you're using it, you should be using it more. If you're not using it, give it a try. And thank you very much for listening.